Welcome to section 2.3, day 1, AP Calculus. And these are our 3 cats. Penny, Lane, and Barry are actually my son's cats, but Biggie's our cat. Biggie likes to get in the sink. But anyway, that has nothing to do with continuity, and it doesn't matter because this is fun. Okay, so this is continuous functions, and basically a function that can be sketched in one continuous motion without lifting your pencil. It sounds easy, doesn't it? So if I have a function right here, I don't lift up my pencil, it's continuous. If I have a function like this, where I pick up my pencil and then I go on from another point, that's discontinuity. We have several types of discontinuity, which we will talk about in a few minutes. All right, so we're going to talk about continuity at a point. Now, in this little graph, the red graph here between A and B, we have interior points, which are points like C, anywhere inside A and B, and then we have the endpoints, which are A and B. So we're going to talk about continuity at both of those points. Basically, continuity is when you have, you have a limit. Okay, I need to change the screen so you can read it. If you have a limit as x goes to c, some point that's on the interior, we are calling it c, of the function. If you have this limit, that means the left-hand limit has to equal the right-hand limit, right? And so if that limit equals the actual value of the point, then it is continuous. Okay, but you have to have that limit. Left-hand limit has to equal right-hand limit, which means your general limit exists, and then that has to equal the function value. All right, the same thing is at the endpoints. The limit as x goes to a, which is the left endpoint, from the positive side, because this only has a limit from the positive side, of this function has to equal the function at the point A. All right, so the right-hand limit has to equal the function value. And then for B, the limit as x goes to B from the negative side of the function has to equal the function value at B. So that's for endpoints, the 2 endpoints. So then we would say that these functions are continuous at point A or continuous at point B. Okay, that's continuity at a point. Okay? Now, we're going to have to find points of discontinuity, or find points of continuity. And here are the requirements for a function to be continuous at a point. Number 1, left and right hand limits have to exist. Left and right hand limits have to be equal, and the left and right hand limits must equal the value of the function at the point. If a function f is not continuous at a point C, it's called discontinuous, and it's a point of discontinuity. Sounds a little bit redundant, but that's definitions. Okay, so these are 4 types of discontinuity. All right, so if you're not continuous, you must be discontinuous. So the first one is a removable point. All right, that's where you have a point. Some people also call this a point discontinuity. Either one is fine. Removable point. The next one is called a jump, where your entire function actually jumps to another level. Okay, so that's a jump discontinuity. We also have 2 other types, infinite discontinuities and oscillating. So an infinite discontinuity is when you have like an asymptote. Okay, so at x equals 0 for this function, we have a discontinuity. All right, it's continuous everywhere else, but at x equals 0, it's got a discontinuity. And the same thing happens with the function sine of 1 over x. This function actually has a discontinuity at x equals equals 0. And this. So therefore it has also a hole at x equals 0. All right, so those are 4 different types of discontinuities. Let's take a look at some examples, like problems you will be doing, finding points where the function is continuous and discontinuous. So sometimes it's easier to say that this function, if we call it f of x, we'll call it f of x, is continuous from, we have a 0 to a 7. It's continued from 0 to 7, except for these points. X equals 2. We have a jump discontinuity. At x equals 5, we have a point discontinuity or removable. I guess I should write these down. Actually write the type since I make you do that on the test. X equals 2 is a jump discontinuity, point removable discontinuity, and gosh, I guess that's it. The rest of it is continuous. All right, so you should be able to write down the points where it's not continuous and why. All right, so here we have a graph, 1 over x plus 3 squared. So if you graph this, you have a little graph that looks like this. And this point right here, or this point, this asymptote, is x equals -3. All right, so you can say that this graph is continuous. Trouble spelling that word, from -infinity to infinity. It's not a closed interval. The parentheses say closed, whereas on the last we had I'm sorry, that's an open interval. This is closed interval because we have the brackets. These parentheses signify an open interval because infinity is in a defined place. And so we have the entire domain except for x equals -3, which is an infinite discontinuity. Okay. Now, we have another important note. This important note says, be careful using calculator graphs. Pixels may connect, but a point of discontinuity may exist. So when you zoom in, you may find that there are points of discontinuity. Now let's see how this works algebraically. We can actually factor this, x minus 5 times x plus 3. So we actually end up with 1 over x minus 5. All right, but that doesn't mean we still don't have a discontinuity at x equals -3. So, all right, so if we were to graph this, we would see that, I've actually already plugged it in here, x plus 3 over x squared minus 2x minus 15. If we graph that, we see that at x equals +5, we have an infinite discontinuity. And at x equals -3, we don't see anything, okay? So, but at x equals -3, we have a point or a removable discontinuity. Okay, so that means that this function would be continuous on the entire domain, -infinity to infinity, except for those 2 points. Okay? So just be careful about looking at your calculator, because if I look at this screen, I say it's continuous except at x equals 5, which is not necessarily true. Now, one thing we could also do is fill in this point and have a continuous function. All right, so we will talk about doing that as well. Signing off from section 3.3, day 1.